Tonight we are going over chapter 8, which is the second aspect of estimation, that is hypothesis. A hypothesis is a statement about a parameter which is either true or false, but not both at the same time. In hypothesis testing, we are going to test a statement about a parameter using statistic obtained from a random sample. There are generally two types of hypotheses in statistical hypothesis. The null hypothesis, which is generally the statement which is being tested, involves an equality. So if a claim is made about a parameter, and that claim involves statements such as less than or equal to, or greater than or equal to, then that statement is a null hypothesis. The alternative hypothesis is the opposite of the null hypothesis. For instance, if we believe that the average height of professional male basketball player is taller than it was 10 years ago, we will use it as an alternate hypothesis, and it is denoted by H1, and we write mu is greater than 6.5. In this case, the null hypothesis is H0, mu equals to 6.5. Even though the null hypothesis could be greater than or equal to, or less than or equal to, we will generally express it as an equality to reflect the fact that it involves equality. A car manufacturer advertises that its new subcompass model gets 47 miles per gallon. Let mu be the mean of the mileage distribution of these cars. State the null and alternate hypothesis. H0 will be mu equals to 47, and H1 will be mu is less than 47. In this statement, when we say that the car can take up to 47 miles, that will actually mean that the average miles is 47 miles or higher. So that is why the alternate hypothesis is that the average miles is less than 47. There are two types of hypotheses, or three types generally, not two, three types. We have the left, the right, and then the two-tail hypothesis. The alternative hypothesis is generally what is used to determine if a test is a left tail, a right tail, or a two-tail. Most generally, we will speak about one and two-tail hypothesis, and the one-tail hypothesis is divided into two subtypes, that is left and right. So in this slide, we are expressing the alternative hypothesis that is a reflection of the type of test we are dealing with. So the null hypothesis for all tests is mu equals to k. We always write it mu equals to k, even when it is mu is less than or equal to or greater than or equal to. We write it as mu equals to k. For a left tail, the alternate hypothesis is mu is less than k. For a right tail, the alternate hypothesis is mu is greater than k. And for a two tail, the alternate hypothesis is mu is different from k. So these are the 5 steps in hypothesis in testing. First step, identify the claim and state the hypothesis. In the second step, you will compute the test value using the hypothesized parameter. The third step, you will compute the p-value or the critical values. And you will make a decision. This decision will be based on either rejecting the null hypothesis or not rejecting the null hypothesis. And then you will draw a conclusion. Hi, Andy. Welcome back to the class. I'm just starting. So I was discussing about hypothesis testing and essentially at the beginning. So there are two types of errors in hypothesis testing. Let me say again essentially what I have discussed so far. Hypothesis testing consists of testing a statement made about a parameter of a population. There are two types of hypothesis. The null hypothesis, which involve equality, that is less than or equals to, greater than or equals to, or equals to. It generally represents the state in which things are the way it has always been. There is no change. The alternate hypothesis is the opposite of the null hypothesis. In that hypothesis, the parameter is either less than, greater than, or different from. In each of them, I can use the mean to represent each of the cases. So at this point, we want to discuss the errors in hypothesis. So the mean is at the middle. And we may say that the null hypothesis is the mean is greater than or equals to a certain value. In that case, if the mean is greater than or equals to the value that we have here, it is the null hypothesis. So if it is to the right side, that is fine. If it is to the left side, we may still feel like it is due to an error for the mean to be to the left side. Let me put it here. So if we have mu is greater than or equal to k, then we will write k here. Then we take a sample and compute the sample value corresponding to the mean. If the statement about the null hypothesis assumes that mu is greater than or equal to k, it will mean that the mean is above k. But because it is a sample, we can accept that it is below k. But we will set a point that we are going to call the critical point, which will be ZC, generally a negative number, from which if the sample mean is less than this ZC, is less than this value, let me call it A, then we will say we reject the null hypothesis. And this area is called the rejection area. Let me say it again. We start with a null hypothesis, and we assume that the mean is greater than k, so we place k here. So we take the sample mean, and if it is above k, we do not reject the null hypothesis because it is consistent with the null hypothesis. If it is below k, we may still not reject the null hypothesis, assuming that it could be due to sample error. But if we move below k until we reach below a certain value A that we will call Z, or the critical value, we will say that it is too small to be consistent with the null hypothesis, and we will reject the null hypothesis. This is the general idea behind testing hypothesis. So we assume a value for H0. That is why we are going to always write H0 as equality. Mu is equal to k. And then we test that value, having in mind what the actual statement about the parameter was. And we will say this is a left tail. If it was that mu is less than or equal to k, then when it is to the left of K, we will still be okay. We will not reject the null hypothesis. But if it goes to the right side of K, we can still say it's due to a mistake until we get into a critical value, after which we will feel like the difference is too much to be due to an error, and we reject the null hypothesis. For a two-tailed test, it's generally mu equals to K. And in that case, it could be less than or greater than. So we have two critical points whenever we have a two-tailed test. So in testing the null hypothesis, we can encounter two types of error, which will be represented on a table here. So we will assume that H0 is true or H0 is false. If H0 is true and we take the decision not to reject H0, there is no error. But if we take the decision to reject H0 when it is true, we make a type 1 error. If H0 is false, and we do not reject H0, we make a type 2 error. If we reject H0 when it is false, there is no error. I'm going to show this again using the whiteboard or a different form. So here I will say H0 is true. And here I will say H0 is false. And here I will say reject H0, and here do not reject H0. So if H0 is true and we are here and we reject H0, we call it a type 1 error. And here is a good decision if H0 is false and we reject H0. If H0 is true and we do not reject H0, it's also a good decision. And here we will have a type 2 error. Type 1 error and type 2 error are like a balanced type of situation, in a balanced type of situation. If we take the example of a visit to the doctor or a visit to the doctor, we will say H0 is true when the patient is healthy. We will say rejecting H0 will mean giving treatment to that patient. If we give treatment to a patient who is healthy, that is a type 1 error. If we do not give treatment to a patient who is healthy, that is good. But if a patient is not healthy and we give him treatment, that is a good decision. If a person is not healthy and we do not give him treatment, that is a type 2 error. So if we take two doctors, one that does not want to send, this one will give treatment to a healthy patient because he does not want to send the patient without treatment. That is a type 1 error. There is the other doctor who will not give treatment to the patient when the patient is healthy. Choosing to make a decision between a type 1 and a type 2 error, if you want to reduce the type 1 error, you will be increasing a type 2 error. For example, if you are inclined to give treatment, you will likely give treatment to a healthy patient. If you want to avoid giving treatment to a healthy patient, you will likely send an unhealthy patient home without. So that is the contrast between the type 1 and a type 2 error. We can also use a court situation to illustrate this. In a court situation, a type 1 error will consist of, H0 is true when a person is innocent. Reject H0 will be considered to convict the person. You make a type 1 error when you convict an innocent person. In the effort to avoid to make a type 1 error, that is, you do not want to convict an innocent person, you will likely have to send home a guilty person. Let's go back to PowerPoint. So the probability of committing a type 1 error is called the level of significance of a test, and it is denoted by alpha. And the probability of making a type 2 error is denoted by the Greek letter beta. And the probability of not committing a type 2 error is called the power of the test, and it's denoted by pi. We will more in the course use alpha, the level of significance, to determine the critical values or to make decisions. So I encourage everybody to use a TI-83 calculator because that is going to do the computation of the test value and the p-value, which we will be using to make our decision in hypothesis testing. The p-value is the probability that z is either less than a test value for a left tail test or greater than the test value for a right tail test. So here again, I'm going to explain. I'm going to explain what the p-value is using a normal distribution. So we set that the mean is, let's say, k. We start with the mean equal to k. And let's assume that we are dealing with a null hypothesis that mu is greater than or equals to k. We set a here as the critical value. We want to determine the position. We want to determine the position of the sample statistic with respect to A. So what we will do is we will compute the area to the left of the test value. If the sample mean is here, and we compute the area to the left of the sample mean, we can use that area to the left of the sample mean and compare to alpha. Alpha is the area for the critical value. If I know the area to the left of X bar, I can compare it to alpha to determine if this X bar is in the critical region or not. That area to the left of X bar is called the p-value. For a right tail test, we will be talking about the area to the right of the test value. So we are going to decide based on the p-value. If p is less than or equal to alpha, then the statistic is in the rejection region. We reject H0. And if p is greater than alpha, we do not reject H0. So P is the area to the left of the test value. If that area is small, let's say for that area to be small, if that area is smaller than alpha, then the test value will be in the rejection region. If it is greater, it will be like it was before, outside of the rejection region. So let's go back to the PowerPoint to look at the decision. If P is less than or equal to alpha, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. For our conclusion, we may fail to reject the null hypothesis. That is, there is not enough evidence in the data to justify the rejection of H0. This means that we retain H0 with the understanding that we have not proved it to be true beyond all doubt. When we reject H0, there is enough evidence in the data to justify rejection of H0. This means that we choose the alternate hypothesis H1 with the understanding that we have not proved H1 to be true beyond all doubt. When we get to examples, then we will be able to understand this better. So, as I mentioned before, to test hypotheses, we use either the critical value or the p-value. For this course, I encourage you to use the p-value because your calculator, the TI-8384, will be able to compute the test value and the p-value for you, and you just want to use it to make a decision. Example, sunspots have been observed for many centuries. Records of sunspots from ancient Persian and Chinese astronomers go back thousands of years. Some archaeologists think sunspot activity may somehow be related to prolonged periods of drought in the southwestern United States. Let X be a random variable representing the average number of sunspots observed in a 4-week period. A random sample of 40 such periods from Spanish colonial times have the following data. We have the data here. We can use the data to our calculator as we did in chapter 7, or we can use the statistic. We also have the statistic, and at this point, we are going to use the statistics. The sample mean, which is a statistic, is 47, and the population standard deviation is sigma equals to 35. It is thought that for thousands of years, the mean number of sunspots per 4-week period was about mu equals to 41. Sunspot activity above this level may or may not be linked to gradual climate change. Do the data indicate that the mean sunspot activity during the Spanish colonial period was higher than 41? Use alpha equal to 0.05. So in this section, we are testing hypotheses about the mean when sigma is none, like in the case of this example. When sigma is none, we use the Z distribution as we learned in chapter 7. The claim here, which we often need to identify, is the mean sunspot activity during the Spanish colonial period was higher than 41. We are going to use the data provided to test this claim. So because the claim is mu is greater than 41, this claim will be H1, and H0 will be mu equals to 41. Next, we compute the test value. The test value is the Z-score of the sample mean. Remember that the sample standard deviation for the sample mean, the standard deviation for sample mean is sigma over square root of n. So this is how we will compute the test value manually. But at this point, I would encourage you, Andy, do you have your TI-8384 calculator? Do you have your calculator?
I do, yes.
Okay, so we are going to use calculator here. We will go to start. I think at this point, you know how to go to start. Go to start and then test.
Okay.
The first option is the z-test. We use the z-test because sigma is none. In all of what we are doing, we assume that the population is normally distributed or the sample size is at least 30. In this case, the sample size is at least 30. So in both the T and the z-test, we need those two conditions. But what makes the decision whether to use the z or the t is the provision of sigma. So we are going to use statistic for now. Though we have the data, we are going to use statistic to move faster. So the mu0 here is the value of the mean at h0, which is 41.
Okay.
Then sigma is the standard deviation of the population, which is 35. Now the sample mean, we can see the sample mean here to be 47. Sample mean is 47. Sample size is 40. And we have to decide whether it's a left or a right tail test. This is a right tail test because mu is greater than 41 at H1. H1 is what we use to determine if it is a left or a right tail test. So we are going to choose mu is greater than mu0 and press enter, then calculate.
Okay, got it.
Okay, so you can see z equals to 1.08.
Yes.
You will have this type of question on quizzes and exams. So once you know how to use your calculator, if I ask you for the test value, it's 1.08. Now to make a decision, we will use the p-value. The p-value here is 0.14, as you can see from your calculator, p equals to 0.14.
Mm-hmm.
So we are going to look at alpha, which is the level of significance of the test. So on this slide, we were told to use alpha equal to 0.05. If you were not using calculator, then you will have to read the area to the right of z equals to 1.18 as you did in chapter 6. That's the p-value, the area to the right for a right tail test, the area to the left for a left tail test, and then double the area either to the right or the left of z for a two tail test. But when you have a calculator, that spares you to do that, from doing that. So here p equals to 0.14, which is greater than 0.05. So we do not reject H0. We do not reject H0 because p is greater than alpha. So that means at this level of significance, there is not enough evidence to support the claim that the mean, we do not think that the average sunspot activity during the Spanish colonial period was higher than the long-term mean. So what we have gone through 5 steps. The first step was to state the hypothesis. Mu equals to 41, mu is greater than 41 is the alternative hypothesis, and which is the claim. Then we use our calculator to compute the test value, which is 1.08. We can either read from the z distribution table or from our calculator. The p-value is 0.14. The decision is to compare this p-value to alpha. If it is less than or equal to alpha, reject H0. Otherwise, do not reject H0. In this case, it is greater than alpha, so we do not reject H0, meaning there is not enough evidence to support the claim. So this slide gives us the steps in using the calculator. So now, when sigma is unknown, As we did in chapter 7, we use the t-distribution. The condition for using the t-distribution is, first, a common condition to both t and z, either the population is normally distributed or the sample size is at least 30. If sigma is unknown, then we use the t-distribution with degree of freedom n-1. Here again, I advise you to use your calculator. The test value is similar to the one for the z distribution, but sigma is replaced by s. So we can use our calculator to do this test. The critical value for the t-distribution is obtained from the t-distribution table, which if you are using calculator, you don't need it. And you will need to decide whether you are using a one or a two-tail test. And if it is a one-tail test, whatever you read there, you will take the negative number as the critical value. So this is an example. The drug 6-MP is used to treat leukemia. The following data represent the remission times for a random sample of 21 patients using 6-MP. The sample mean, let's just practice using data for this test. So to enter data into the calculator, you go to Start and press Edit or Enter. Then we are going to enter the 21 values in L1.
Alrighty, I entered the data points.
You enter all the values?
Yes.
Okay, I'm still working on it.
Oh, sorry.
I am slow in typing. Okay, so now we are going to come back to the calculator later.
Okay.
So we have the data and we will be asked to assume the distribution is mount-shaped and symmetric. That is, it is normally distributed. A previously studied used drug treatment had a mean remission time of mu equals to 12.5. Do the data indicate that the mean remission time during the drug, using the drug 6-MP different from 12.5? So this is the claim. The mean remission time is different from 12.5. Use alpha equals to 0.01. So we are going to state the hypothesis. H1 is mu is different from 12.5 is our claim, and H0 is mu equals to 12.5. So this is a two-tail test because different could be less than or greater than either way. So it's a two-tail test. We should remember that as we are using our calculator. So now we go, the first question is, what distribution do we use for the sample test statistic? Because the standard deviation of the population is not provided, we will use the t-distribution. So you press Start on your calculator and then use option 2, which is t-test. Now we have data, so go to data and press enter when your cursor is on data. Now mu0 is 12.5. We use L1, so if you have L1 there, nothing to change. Now we need to decide what type of test we are using is different from. We use different from, so we press enter for different from, and then calculate.
Okay, got it.
Okay, so we have the test value to be 2.1,
Mhm.
and the calculator will provide us with the p-value. Here on this table, you have the p-value is generally estimated in your textbook because you are using the t-distribution to find it. So don't worry, you already have the exact value, which is what you have on your calculator. What is the p-value you have from your calculator?
I have 17.0952381.
I mean the p.
Oh, my bad. Sorry. 0.048.
0.048. So we are just going to compare this to alpha. Remember the alpha was 0.1. We were told to use alpha equal to 0.1. I'm sorry, 0.01. Alpha is 0.01. So we will compare this to alpha. If you were to use the distribution, I encourage everybody to use calculator. If you were to use the t-distribution, you will identify the degree of freedom and then look for the two numbers that enclose the test value. Our test value is 2.1. It is greater than 2.08, and it is less than 2.52. And then you move up to find, because we are using two-tail, these two numbers, 0.05 and 0.02, will enclose the p-value. That we will say p-value is greater than 0.02 and less than 0.05. Anyway, that's not our problem now because you get the exact value of the p-value from the calculator, which we will want to compare to the alpha. So we compute p-value to be 0.04. This p-value is greater than 0.01, so we do not reject H0. So based on this information, the new drug is not different from the previous one. So we say at 1% level of significance, the evidence is not sufficient to reject H0 based on the sample data. We cannot say that the drug 6-MP provides a different average remission time than the previous drug. So simply put, we will say there is not enough evidence to support the claim that the new drug is different from the old one. We are going to encounter a situation in which sometimes we use the word reject in our conclusion. Sometimes we use the word support. But for the decision, either you reject H0 or you do not reject H0. The decision is always about H0. After making that decision, your conclusion is about the claim. You either support the claim or you do not support the claim. You reject the claim or you do not reject the claim. When the claim is H1, we either support or do not support it. If the claim happens to be H0, as you will see sometimes along the line in the course, we either reject it or we do not reject it. In most cases, the questions in the problem is going to lead you into what conclusion to have. For example, in this problem, the question was, do the data indicate that the mean remission time using the drug 6-MP is different either way from 12.5 weeks? Your answer will be at 0.01 level of significance, the data do not indicate that the mean remission time using the drug is different. So this part, using critical region, I generally skip it, but you can go over it quickly. When we use the critical values, that means we find the Z or the T value so that the area to the left, the right of it is alpha. Then when we have our test value, we use the critical value to determine if the test value is in the critical region or not. For example, as we were doing in example 3, we find the test value to be 1.08 and alpha was 0.05. And we will discover that this was a right tail test. So we want to find Z so that the area to the right of Z is 0.05. So that value of Z is 1.64. So we will compare 1.08 to 1.64. Let me use the whiteboard to represent it. So if we were, I'm going back to the example for the Z test. So alpha was 0.05. The critical value will be, this is alpha. And the critical value is the value of Z, which is here. This is the critical value. Now the test value, we found it to be 1.08. So we compare it to 1.64 and it is less than 1.64. So that means it is somewhere here. So the test value is not in the critical region. What we did using the p-value as it is in your calculator is to find the area to the right of Z and compare it to alpha. I just want you to know what it means to use the critical value. I encourage you to use the p-value because the critical value require a table. So it will always require that you go open your textbook to look at that table. But it's the same procedure as using the p-value. Test for proportion. In testing for proportion, we use the Z distribution if the number of success is greater than 5 and the number of failure is greater than 5. So the tests are similar to what we had before. Either the proportion P is equal to K for null hypothesis. For the left tail, P is less than K. For the right tail, P is greater than K. And for a two tail, P is different from K. So recall that the standard deviation of the sampling distribution of sample proportion was square root of PQ over N. We did this in chapter 7. You don't really need to know the formula because you can use your calculator. So this is how we find the test value. So let's do this example. A team of eye surgeons has developed a new technique for a risky eye operation to restore the sight of people blinded from a certain disease. Under the old method, it is known that 30% of the patients who undergo this operation recover their eyesight. Suppose that surgeons in various hospitals have performed a total of 225 operations using the new method and that 88 have been successful. Can we justify the claim that the new method is better than the old one? Use 1% level of significance. So the old method has a 30% rate of success, that is P equals to 0.3. Saying that the new method is better than the old one will mean that the proportion of success with the new method is greater than 0.3. So it will be H1, P is greater than 0.3, and H0, P equals to 0.3. Let's use our calculator to do the test. If we were to do it manually, we will have to find the proportion of success, the proportion of failure, and so on. So we go to the calculator, go to Start, Test, and we will use option 5, which is one proportion Z-test. P0 is the null hypothesis, P equals to 0.3. Then the number of success here is X, which is 88. And the number of trials, or the sample size is 225. Remember that the alternate hypothesis was P is greater than 0.3. So It's a right tail test. So we are going to choose greater than. Are you able to get it?
Yes.
Okay. So the sample proportion is 0.39, as you can see in your calculator. In some of your quiz question, I may just ask you for this sample proportion p hat, which is number of success divided by sample size. Then we can see z equals to 2.95. Z equals to 2.95. And the p-value is, can you tell me what the p-value is?
I have 0.486.
0.4? No.
Yeah.
What is the z? What is the z value there?
Yeah, I have a different one. It's 0.03.
0.03. Okay, let's start over.
Okay, thank
Go to
you.
start. Then choose option 5, test, and option 5.
Okay.
So what do you have for P0?
0.39.
No, it's 0.3.
Oh, okay.
0.3. What is on H0? That's what you use on P0, or mu0 is what you have on H0. And what is your X?
88.
And N?
225.
Okay, so you now choose greater than and calculate.
Oh, okay, gotcha. There we go. Thank you.
You're welcome. So we go down, we have the Z equals to 2.95. As I told you, calculator have more exact than when you are doing it manually. And then the p-value is 0.014. And if you are reading the table, it's 0.016. Don't worry about those slight differences because the table is fixed. Calculator is using all the details of the numbers that you have. So if you were taking a test and you were asked for the p-value, if you see 0.016 and you are on your calculator 0.014, choose that one as the right answer. But that happens mostly with your, it doesn't happen too often that there's much difference, but you might sometimes see slight difference as this one. Okay. So now, P is less than alpha because alpha is 0.01. So we reject H0. And the interpretation of this is that the new method is better than the old one at 1% level of significance. So there is enough evidence to support the claim that the new method is better than the old one. Is it okay with you?
Yes.
Okay.
Thank you.
You're welcome. Last section. This section is the longest one because it is going to take all the 3 tests we have done for 2 parameters. That is, we are going to test the difference of parameters. So we start with the idea of what is paired data. We say that, what was this again? Here is paired difference, I'm sorry, section 8.4. There is another section. There is another section, section 8.5. Paired data. Data are paired. I said it in chapter 7, but we did not do anything on paired data on chapter 7. In chapter 8, we have this section on paired data. Data are paired when they are collected in pair. For example, left and right at the same time, before and after, something like that. So I'm going to skip this explanation. You can read it later. So when we have paired data, what we usually do is to take the difference between the values in the pair. We have before and after. For example, I might want to test the strength of left and right hand and decide whether left hand is stronger than right hand for all individuals. So what I will do is that I will take each individual, measure the strength of his left hand and the strength of his right hand, and take the difference. That is left minus right. Depending on what I want, we use the convention of before and after. So D is before minus after. What comes first minus what comes after. Once we do that difference, we will transform our paired data into a single data called the difference of the pair. And the test goes exactly as we did the t-test for single data before. So that difference could be equal to 0 when there is no difference, less than 0 when the previous is less than the after, B less than after B less than A means B minus A is less than 0. Greater than 0 is B is greater than A. B minus A is positive. And different from 0 if B minus A is different from 0. That's the difference is different from 0. So what we do here for paired data is that we take the difference of the paired and then test it using the data, using data as if we were having a single data. I usually also use the Excel here. I'm going to use Excel and calculator. Let's look at this example. A team of heart surgeons at St. Anne's Hospital knows that many patients who undergo corrective heart surgery have a dangerous buildup of anxiety before their scheduled operations. The staff psychiatrist at the hospital has started a new counseling program intended to reduce this anxiety. A test of anxiety is given to patients who know they must undergo heart surgery. Then each patient participates in a series of counseling sessions with the staff psychiatrist. At the end of the counseling session, each patient is tested to determine anxiety level. And we have the results here. We are going to come back to this, enter it into Excel or calculator. Higher score means higher levels of anxiety. Assume the distribution of differences is mound-shaped and symmetric. From the given data, can we conclude that the counseling session reduced anxiety? Use a 0.01 level of significance. So here the claim is that counseling reduces anxiety. So anxiety before counseling is higher than anxiety after counseling. That will actually mean that B minus A is positive. That is the claim. So I am going to, this is, you can see the data here, anxiety before, anxiety after, even from observation, you can see that in general, anxiety before counseling is bigger than anxiety after counseling. I'm going to use Excel here. Can you use Excel?
Yes.
Let's use Excel.
Okay.
We are going to use calculator if you want, but I like at this point for students to be able to use Excel. So, because we cannot at the same time have Excel and the PowerPoint, you are going to copy what you see on my Excel, unless you have the PowerPoint before you. So before is 121. $93. Then after, so I have the data on of before and after here. Do you have the data?
Yes.
Okay. Now you click on data, then data analysis. And I will go down and you will see here t-test for paired two sample for means. And I want you to also observe there that each time you have data, you can use Excel for these other three tests that we are going to do. So this is paired data. When the data are given in pairs, you use the t-test for paired data. So this is t-test for two sample, assuming equal variances. On your calculator, you were seeing in chapter 7, I told you that you have pooled when you are doing t-test for two population, pool and no pool. You use pool for equal variance. If you are not mentioned that the variances are equal, then you will use the two sample for unequal variance, and this is Z for two sample or two samples. You can use Excel only when you have data. If you have statistics, which is less likely anyway, so with statistics, you can use your calculator. But with Excel, is essentially data. With data, you can use your calculator. With statistics, you can also use your calculator. But with Excel, essentially, you only use it when you have data. So I will choose t-test paired two sample. Here is OK. So range variable 1, I will highlight A1 to A9. Variable 2, I will highlight B1 to B9. Hypothesized mean for difference here is 0. And we will choose an output. I can choose D2. Are you with me?
Yep.
Okay, then we click OK. Yeah, to read this, we know that we were testing the claim that counseling reduces anxiety, meaning that anxiety before the counseling is greater than anxiety after the counseling, which actually means it's a right tail test. So we are doing a one tail test. So the p-value, the test value is here, 4.36 is the test value, and the p-value is here, 0.001. So in this, using Excel, you have the option of a two-tailed test as well. Here is when it is, if it is a two-tail, because Excel will not know if what you are doing is two-tail or one-tail. That you should know. We will go back to the PowerPoint and continue from having in mind what result we have here. So the method that is used manually, if you don't have Excel, is that you take the difference between B and A, as I told you, and you use this data in your calculator or whatever mean you want to use as a single test. So we have here, the test value is 4.36. Remember on statistic, we had it on Excel, we had it as 4.36. And the p-value is not generally computed here, as I told you, is a range of values, but we know from Excel that it is 0. Do you have it on your Excel? P-value, can you tell me what is the p-value? Do you have your Excel?
Sorry, I was still muted. It is 0.00122026.
Great, that's good. I want to make sure you can read it. So that was p-value, which here, as I told you, your book will be discussing it as a range of values. You have the exact value, which you will compare to 0.01. You can see that this p-value, 0.012, is less than 0.01. So we reject the null hypothesis, and we can conclude that at the 1% level of significance, there is enough evidence to support the claim that anxiety counseling actually reduces anxiety level. Now, 8.5 is about testing for independent values, independent samples. We are going to test the difference when sigma are known and when sigma are unknown. Based on what we have done before, I don't really need to comment much about this. We have done tests with either sigma known or sigma unknown is essentially the same. Now we are going to be using two samples rather than one. So the test value is here. As I said before, you don't really need to memorize this formula because you are using calculator. Let's use this example. We are just going to do like 3 examples for each case. A consumer group is testing CAM stoves. To test the heating capacity of a stove, it measures the time required to bring 2 quarts of water from 50 Fahrenheit to boiling at sea level. 2 competing models are under consideration. 10 stoves of the first model and 12 stoves of the second model. And we have the following data. The following statistics. So we will come back to it. Assume the time required to bring water to boil is normally distributed for each stove. Is there any difference between the performance of these 2 models at 5% level of significance? So here, we have the null hypothesis and the alternative hypothesis. We focus more on alternative hypothesis because the null hypothesis is always equal to. So if there is a difference, it means mu1 minus mu2 is different from 0. We want to test this at 0.05 level of significance. We will use the calculator. I come back here. Let's use the calculator. We go to start, then test. Option 3 is 2 sample z-test. You use the z-test when sigma are provided. So we are going to use statistic. If it was data, we will enter the data in L1 and L2. Sigma 1 here is 2.5. Sigma 2 is 3. Sample mean 1 is 11.4. Sample size 1 is 10. Samples 2 mean is 9.9. Sample size 2 is 12. So the test was whether they were different. So we are just going to take different, the first option here, and calculate. So if you are working manually, that is without a TI-83, 84 calculator, you will want to find the difference between the sample mean x1 minus x2, and then compute the z value for that difference using the standard deviation of the population. We will have the z value to be 1.28, and the p-value is 0.2. This p-value is clearly greater than 0.5, so we do not reject H0. So at the 5% level of significance, the sample data do not indicate any difference in the population mean times for boiling water for the two-stove model. Are you getting the right answer from your calculator?
Yes.
Good.
Yep.
So when sigma are unknown, we use the T distribution. Just as I said before, when the variances are the same, we use a common estimate for the common variance, and we call it the pooled variance. Or we use, when we don't know it, as it happened most of the time, we use the formula which is here. So here again, two competing headache remedies claim to give fast-acting relief. An experiment was performed to compare the mean length of time required for bodily absorption of brand A and brand B. 12 people were randomly selected and given an oral dosage of brand A. Same thing for brand B. So we have the statistic here, which we can enter into our calculator by going to Start, Test, and we will go to two-sample t-test because the sigma are unknown. We have the statistics. Sample mean 1, 21.8. Sample standard deviation 1, 8.7. Sample size 1, 12. Sample mean 2, 18.9. Standard deviation 2, 7.5. And we have. So I cannot yet decide because we have not completed reading. Have you entered those values?
Yep.
Okay. Past experience with the drug composition of the two remedies permits researchers to assume that both distributions are approximately normal. Let us use a 5% level of significance to test the claim that there is no difference between the two brands in the new time required for bodily absorption. So we want to test the claim that there is no difference. Observe here that this claim is H0 because the claim is there is no difference. So we are going to choose the first option, alternate hypothesis is different from. Then no pool because we did not have the information whether or not the population variance were the same. Most of the time, I mean, in this course, we are always having no pool so that there shouldn't be any confusion. And now calculate.
Got it.
Okay, so what is the test value?
0.87.
Okay, 0.87, good. So the p-value What is the p-value?
0.39.
0.39. We can see that this p-value is really greater than 0.05, so we do not reject H0. As we do not reject H0, it means there is not enough evidence to reject the claim that there is no difference between the drugs. At 5% level of significance, there is insufficient evidence to conclude that there is a difference in mean times for the remedies to reach the specified level of bloodstream. Testing the difference between proportion is essentially the same thing. We are going to use calculator again, but with a little difference here for those who don't use calculator. We are going to, because as we are doing the difference, we don't know the population proportion. So we are going to find an estimate for a common proportion, which we will call a pool proportion, by putting the two samples together and finding a common proportion of success, which is number of success of both divided by sample size of both put together. This is going to be used in the formula for the test value. You don't really need to worry about this because we are going to use calculator. So let's look at this example. The Mackcheck County clerk wishes to improve voter registration. One method under consideration is to send reminders in the mail to all citizens in the county who are eligible to register. As part of a pilot study to determine if this method will actually improve voter registration, a random sample of 1,250 potential voters was taken. Group 1, there were 625 people in this group. No reminders to register were sent to them. The number of potential voters from this group who registered was 295. This group also contained 625 people. Reminders were sent in the mail to each member in the group, and the number who registered to vote was 350. The county clerk claims that the proportion of people who registered was significantly greater in Group 2. On the basis of this claim, the clerk recommends that the project be funded for the entire population of Mackcheck County. Use a 5% level of significance to test the claim that the proportion of potential voters who registered was greater in Group 2, the group that received reminder. So we are saying that P1 is less than P2. So if P1 is less than P2, we can write either P1 equals to P2 for null hypothesis, and then P1 is less than P2, or P1 minus P2 is less than 0. So remember that actually means that when you are using the calculator, you will use a left tail. So go back to this information. And we want to enter this information first before we move on. We go to Start, Test, and we are looking for two proportion z-test, which is option 6, two proportion z-test. So X1 is the number of success for the first group, which is 295. N1 is the sample size, 625. X2 is 350. And N2 is also 625. So we say P1 is less than P2. And we calculate. Let me know when you are done.
All set.
Okay. So what is the test value?
The z-value, oh, it's sorry, negative 3.11.
Negative 3.11. That's the test value. So
Yeah.
with that, you find the p-value.
9.26.
Okay. It's not 9.26. It's 9.26. If you look towards the end of it, you will see a minus 4. So that is 9.26 divided by 10,000. That is 10 raised to power 4.
Gotcha.
So it's 0.009. You want to be careful about that. When the decimal is too many, generally the calculator expresses it as a negative power of 10. So P is actually less than 0.05, so we reject the null hypothesis, and we say at a 5% level of significance, the data indicate that the population proportion of potential voters who registered was greater in group 2, the group that received reminders. So I will stop here. The next part of it is how to use critical value. The main aspect of critical value is using the level of significance to find the boundaries of the critical region. So just as we said in 8.1 and 8.2, when you have alpha, you can either use the Z or the T. For the Z or the T, you take the Z value, so that area to the left is alpha. For a right tail test, so that area to the right is alpha. And then once you compute the test value, you compare it to the critical value to see if it is in the rejection region or not. I advise everybody in this class to use calculator, because doing this work manually will take you a longer time. So this is the end of chapter 8. Do you have any
Thank
questions?
you.
You're welcome. So if you have questions, send me an email. Start doing the homework first. Get used to your calculator. It is much faster. Practice using your calculator when you are doing your homework. And if you have questions, send me an email. Have a good evening.
Thank you very much. You too.
Thank you, Andy.